Hello, and welcome to part 3 of homework 4 here, where I'll be performing a von Neumann stability analysis to show theoretically the limit of stability on the explicit differencing scheme used in part 2. And so, if you haven't realized, we used a finite differencing method to derive our temperature profile for part 2, and the one that we used was an explicit method. And so with that came some issues when we tried to adjust our time step, and that was the fact that it limited it to 0.5. And so we'll be seeing why it did that now. And so let's jump right into it. So this begins with our differential. So let's write that down. It was alpha second partial derivative with respect to position is equal to partial derivative of temperature with respect to time. And so these partial derivatives, in theory, have almost an infinite amount of solutions. And to get to those solutions, there's always some methods that are derived, and you solve it by hand most of the time. And so these solutions are usually represented with an integral, even summations even. And so instead of doing all that, there is one particular solution that can prove this limit. And so the particular solution that I'm going to be focusing on is t is equal to the exponential to the I, that's the imaginary, k x to the e negative alpha k squared t. And to prove that this is indeed a solution to this differential, I'll do the derivations here. And so the partial derivative of temperature with respect to position is going to be equal to, bringing it down, that ik e ikx, this stays the same. The second partial derivative is equal to i's multiply negative k squared e to the ikx e to the negative alpha k squared t. Now, got to compare it to the time dependent one. So that will be this won't change. This term won't have any effect. We bring down the negative alpha k squared e to the I kx e to the negative alpha k squared t. And just looking at this, these two expressions differ only by the alpha term, and that's resolved here in the original partial derivative. And so this is indeed a solution, and that's just what I just wanted to prove that real quick. And so, like I said, there are many solutions to this partial derivative. It's just that we will be focusing on this particular one. And just checking my phone cam real quick. All right. And so let's apply this particular solution to our case, in which we have discretized our bar and we have certain temperatures at those counters. And so the temperature at some position count and some time count is going to be equal to e ik. Well, to get the true position, it'll be that j times delta x. And then we do the same thing here. To get the true time, it's going to be n times delta t. And so what do we do with this now that we've applied it to our scenario? Well, like I said earlier, implied, sort of alluded to earlier, we discretize our bar. And so we had sort of derived an equation for that discretization, right? And what was that equation? Well, it was tj plus 1 n r plus 1 minus 2r tj n plus r tj minus 1 n is equal to tj n plus 1. And, well, we can plug this in for that. And, well, before we do that, we can realize that, well, we can derive the same equation. We could derive an expression, I guess I should say, for the position after and before at the same time. And we'll do that. So to get it at the next position step, we just plug in the next position step for the position counter. So we get ik j plus 1 delta x the second term does not get adjusted. Saying j plus 1 inside an exponential is saying that this original exponential, is being multiplied by another exponential of the same terms, and those same terms being ik delta x, thus the plus 1. And so since all the terms are the same to this tjn, besides the extra e to the ik delta x, we can express it as tjn times e ik delta x, since this will equal this. And we apply that same logic to the previous step, in which this becomes j minus 1, and we put it in terms of tjn, and the negative goes up in the exponent. And so now we can plug everything in for this left side in turn, and I'm going to factor out the tjn to get that out of the way. So we get tjn times r e ik delta x plus 1, oh my gosh, minus 2r plus r times e to the negative ik delta x is equal to this next time step. All right, and so where do we go from here? Well, it might not look apparent at first, but we can actually apply Euler's formula. And Euler's formula sort of, I guess, states that you can that e to the ix is equal to cosine x plus an imaginary times sine of x, and e to the negative ix is equal to cosine x. There would be a negative, but since cosine's an even function, that cancels out. So not the case for sine, since it's an odd function, the negative stays. So if you were to add the two, and the reason we're adding the two is because we have that scenario here where we are adding the two, we see that we get 2 cosine x because this term cancels out. So we apply that to our scenario, and we just have to make sure that we keep the variables the same. And so any coefficients will stay on the outside here. So let me write that out again. So it will be 2 times r, because any coefficients stay on the outside, and the exponent goes within the cosine, so k delta x. And we get plus 1 minus 2r, and we get n plus 1. All right, and so then I'll just I'll factor out the 2r, and we get cosine k delta x minus 1 plus 1 is equal to 2 and plus 1. All right, and so our road led to this expression. And so what then? What now? Well, just looking at it, we realize that the temperature at the next time step, to obtain this value, we multiply the temperature at our original time step by some multiplicative value, right? And like I said earlier, we saw that our temperature profile after stepping beyond 0.5, it was going to infinity. And well, that sort of makes sense in the fact that this is being iterated over and over and over, right? And we sort of infinitely, you can say. And well, multiplying our original temperature by anything greater than 1 will make it constantly increase, especially, well, multiplying it repeatedly by a value of greater than 1 will increase it infinitely. Hopefully I said that correctly. And so that sort of explains why we are seeing values close to infinity, right? Our term, multiplicative term here, must be greater than 1. And so we have to constrain that. And so if it's greater than 1, it's going to go into infinity. If it's at -1, it's going to go to negative infinity, which we saw as well. It did go to negative infinity. So we have to make sure that it stays within -1 and 1. So let's sort of write that out as an inequality, right? This multiplicative term must stay within the absolute value of 1. Yeah, if that makes sense. So, I'll write in the back here. So -1 is less than or equal to, because staying the same will increase it to infinity, right? 2r times cosine, k delta x minus 1 plus 1 to 1. All right, so easy algebra, subtract by 1. Is 0. We realize that the maximum value that a cosine function can obtain is 1, and therefore 1 minus 1 will be 0. And since its maximum value is 0, we don't have to worry about this right side condition. So we can focus on this left side here. And so this becomes -2 less than or equal. I'll just rewrite it here. Minus 1. I'll divide the negative out now, so that flips the sign. And I'll apply that negative inside the parentheses. Make sure I'm still recording. All right. My phone cam's still going. All right. Oh, and my mic disconnected. Well, whatever. It's fine. So, divided by it. Then, now we solve by r, because that's where our dt is. And we'll see that, well, r. We'll see the limit through r. So, solving for r, we divide by 2, divide by this term here. So 1 minus cosine k delta x is greater than or equal to r. So we find that the limit for r is defined by this term here. And so, well, what is this term? Well, we don't... I guess I should say, what within this term creates that upper limit? So the only thing that's changing is cosine, right? Cosine, whatever value cosine takes determines the limit for r. So cosine can take a value of either 1, a maximum value of either 1, or a minimum value of -1. So whatever value of k that we choose, whatever position change dx that we assign, cosine will always be either a maximum of 1 or -1. So let's say it takes its maximum value. We get 1 minus 1, 0. R must be less than or equal to infinity. Well, as an upper bound or limit, that doesn't make sense, right? It just means that it can honestly be any real number, right? Any number at all. And that obviously isn't the case. So this can't be the limit value for r. So let's see if it's through its minimum value. And it is. 1 minus -1 is, well, 2. So its limit becomes 1/2. And that was what we saw through our coding. And so how do we get around this problem? We'll see that the solution is implicit differencing, which I'll do in part 4. And so thank you. I'll see you in the next video.